I was not sure about my internet connection, so I pre-recorded the talk. It's pretty short. It's an overview of zkVM that I was designing for the past several months. And the idea here is to give you this short overview and then answer the questions. And so the talk is short, and then maybe the most interesting part is the questions about cryptography, VM parts, performance, whatever is interesting to people. So let's get it started. Andreev, and I designed zkVM at Stellar. Today we'll talk about making confidential smart contracts with speed and style. So our goal is to make something like a blockchain with TLS. So we can use public infrastructures to send money between private actors. The most basic confidential ledger would have some sort of encryption for balances and transmitted amounts, and would require the use of zero-knowledge proofs to prove to the network that transactions do not inflate money supply. But since the blockchain is a decentralized consensus system, it is hard to update to any new feature that you may think about in the future. So we need to permit some amount of programmability so that users can build the features they need on top of it. So to implement such ledger, we define a new transaction format, zkVM. It sits on top of the peer-to-peer network and some consensus protocol, and other things like payment channels, order books, arbitrary contracts. They are all implemented using instructions of the VM on top of it. The best way to think of zkVM is like a fancy parser. Most systems define transactions as hierarchical data structures like XML. Ethereum is programmable, but the programs are stored and executed at the level of a global state machine, and the transaction is more like a single signed procedure call. So zkVM transactions fully describe their effects, but use an imperative programming language, sort of like a PDF. This allows expressing value flow and composing conditions in a more natural way. So let's see how it works. In zkVM, each transaction is a program that moves assets from inputs to outputs. For those familiar with Bitcoin, this is very similar to Bitcoin transaction structure. Unlike Bitcoin, you can also issue arbitrary assets and not just transfer a single built-in asset. The assets travel from one output to another. Now, how do we authorize those changes? In zkVM, each output is an object called a contract, which is frozen in the blockchain state. Access control is done through contracts. Contracts contain a list of items that could be assets or arbitrary data parameters. These items are protected by something that we call a predicate. The predicate can be satisfied by a signature, in which case items are simply unlocked and placed on the VM stack. Alternatively, a predicate can commit to a complex program. User may choose to reveal a branch of the program and VM will execute it. In such case, a subprogram gets a chance to do something with its items. For instance, check conditions, create constraints, lock some of the amounts, and create new ones. Remaining items are left on the stack for the outer program to use. To implement predicates, we use a variant of a taproot scheme designed by Gregory Maxwell and Peter Woolley. The big idea behind the scheme is that multi-party contracts are resolved either through cooperation or dispute. In a happy case, when all parties cooperate, they simply sign for an aggregated public key, making the spend indistinguishable from a simple transfer. But if one of the parties is offline or does not cooperate, the counterparty can reveal the pre-committed branch and permits them to unlock the contract. The predicate also allows choosing a program later, sort of to implement a dynamic linking pattern. So instead of using it to sign a specific transaction, you can instead sign a program that will be executed by the VM. Within such signed program, you can directly perform not only checks, but also asset transfers. So you would effectively be signing a partial transaction without awkward and limited hashing models. This is quite simple, but very powerful model that allows us to build a lot of useful protocols on top of zkVM. Now let's put together transaction contracts and predicates. The transaction does not literally contain inputs and outputs. Instead, the transaction is a program that performs instructions that destroy and create contracts via input and output instructions. The transaction also contains an aggregated cryptographic proof for all operations performed on encrypted data. The verifier instantiates a VM for verifying a single transaction. It is a simple stack-based machine with just a stack and no persistent storage. VM is discarded after transaction execution has finished. Each instruction works with high-level concepts, values, constraints, and it provides both the functionality to the user and also enforces the network rules, like making sure that assets are not counterfeited. Instructions produce two kinds of effects. The first is the constraint system. It is built on the fly by the executed instructions. Constraint system reflects both the network enforced rules and additional custom rules coming out of the contracts. When execution finishes, the entire set of constraints is verified using a single zero-knowledge proof using the bulletproofs protocol. Another effect of transactions is deleting existing outputs and creating new one in the UTXO set. During execution, VM does not change the UTXO set. Instead, all updates to the blockchain state are recorded in the transaction log, which is applied later if execution succeeded. This allows verifying all transactions in parallel and applying changes very efficiently in a batch. So this has been a little bit abstract. So how does the program actually look like? So here's a complete set of instructions in zkVM. These are broken into categories, the ones that manipulate items on the stack, others express arithmetic and Boolean constraints, the group of instructions that issue and move values around, and the instructions to interact with contracts. Let's see a quick example of custom constraints. Let's say we want to enforce that a payment to some address matches some formula. We start by pushing a Peterson commitment to a secret payment amount, alongside with commitments for parameters such as time and price. Then the var instruction allocates variables in the bulletproofs constraint system. You can create arithmetic expressions with these secret variables, with addition, multiplication, and then you can form the Boolean statements and compose them with operations such as eq, and or. And finally, the complete constraint object is added to the constraint system via verify that arithmetizes all the constraints and encodes them in the bulletproofs format. If you take a closer look, then you have a formula, something like that, where you say that P must equal some arithmetic formula or some other condition must be valid. In the zkVM, it looks like this stack machine, pretty straightforward instruction code. After you verified or added the constraints for the variable, for the commitment that you have, you can use it to make the payment imperatively. To do that, we use a borrow instruction that produces a pair of assets, a positive and a negative value. The positive one is locked in a new contract or address. The negative one is simply left on the stack that zkVM forbids from simply destroying. The author of the transaction must combine this negative value with the corresponding positive one using the CLO construction that merges and splits any number of values in the transaction, and also makes sure that the values are not counterfeited or transmuted incorrectly. So this is a very important feature of zkVM. The contracts can directly express their requirements as an imperative program with linear logic, eliminating the entire class of security vulnerabilities like confused deputy. So let's see a few examples of how to build protocols on top of zkVM. Let's start with the payment protocol. The basic payment protocol is implemented as such. Your account is represented by a public key, as usual, but that key is no longer directly visible on the network. Instead, it's uniquely blinded each time you receive a payment. This is very familiar to anyone who uses Bitcoin. To receive a payment, you generate a receiver, a special container that describes the unique destination for the funds. It contains the unique blinded address and also the blinding factors for the asset type and quantity. The sender will encrypt the asset with these keys. The blockchain does not know about accounts, but your node does, or your wallet. So it automatically combines a collection of distinct transaction outputs into a collection of balances. To implement secure control over funds, you can create a multi-signature conditions for secure call storage, for instance, or to implement escrow. Finally, users can cryptographically notarize and verify chains of provenance, so the regulated parties, for instance, can easily get verifiable proofs of source of funds linked to the blockchain data with selective disclosure. And what's interesting is that all of these concepts exist completely off-chain. So why is it important? As Gregory Maxwell said, blockchain is a court. It's a place where settlement and conflict resolution happens. It's not a universal computer. So the private data is not exposed. You have less load on the network. It's easier to program and less complexity in the consensus critical layer. So you can improve software without upgrading the whole network. So now let's take a look at the order book example. Order book is a subset of unspent outputs that permit full or partial lift of the asset provided corresponding payment. The contracts verify the payment and unlock the offered asset, and the matching is performed off-chain at the network layer. How does it look like? A contract contains three items: an asset that we're selling, a price, and a payment address. In the simplest case, the contract has just one clause, lift, which does three things. First, it receives the payment, so it ensures that the provided quantity of the payment asset is delivered to the address. Second, we compute the remainder of the asset that we need to lock back into the same instance of the contract in case it was a partial lift. And finally, the requested amount of the asset is simply unlocked in the transaction, so the author of the transaction can decide where to put it. Finally, let's take a look at how payment channels look like. Payment channel is a two-party state machine that allows rapid balance updates without publishing the intermediate transactions. The message that they sign are effectively security guarantees. When both parties are done, they sign the final payout as the actual transaction and publish it. So all the intermediate transactions are simply not visible in the network. But if parties do not cooperate and one of them decides to exit the channel, it publishes the most recent security guarantee. Since the blockchain does not know whether it is the actual latest version, the contract has a timeout provision. The counterparty can detect the attempt to exit, and if it's the latest version, replace it with a new one. Finally, when there is no new version of the signed payouts and the timeout is over, the payouts can be finalized in the personal addresses of each party. So in zkVM, the only state is the set of unspent outputs or contracts. So we model the state machine using them. First, each state is represented by an instance of a contract, and each transition is a separate zkVM transaction that destroys one contract and creates a new one. So contracts can store not only assets, but arbitrary parameters and have a flexible support for signed messages, so modeling such state machines is very straightforward. So let's compare zkVM to a couple of other designs. Since zkVM is a smart contract engine, it is only natural to compare it to Ethereum first. So when people hear smart contracts, they're used to the Ethereum model, that the blockchain is a global decentralized computer and you can run your custom applications on top of it. zkVM takes a different approach. Blockchain is only used for settlement and enforcement of rules, but not for the storage and processing of users' data. This means that in zkVM, most data is normally off-chain and the remaining data necessary for contract verification is kept confidential. zkVM is deliberately not Turing complete. This makes behavior of the contracts much more predictable and allows making the consensus-critical parts of the protocol simpler and more robust. The complexity of the contract logic is pushed to the end users. Contracts in zkVM are strongly isolated from each other. Transactions do not use global state. Finally, issued assets in zkVM are first-class types that can be manipulated directly and sent from one contract into another. In Ethereum, assets are modeled as entries in a miniature ledger stored inside the blockchain state. This means that your smart contract has to reinvent the ledger rules against double spending, while zkVM enforces them automatically. Finally, let's compare zkVM with Zcash and Monero, two crypto coins aimed at confidentiality. Zcash and Monero are designed very differently, but I would like to show how their common features compare to zkVM. So first, smart contracts in zkVM are part of the confidentiality architecture. In Zcash and Monero, contracts are not part of the privacy design. For instance, in Zcash, one can use contracts in a Bitcoin-style, fully public and traceable transaction, and switch back and forth between clear text transactions and private transactions. The powerful aspect of Zcash and Monero is that they provide graph privacy out of the box, because it is non-interactive. With zkVM, the best you could do is a coin-join protocol by mixing your payment with others interactively. However, the big improvement to the graph privacy in Zcash and Monero comes with a high cost and scalability. zkVM requires very little storage, which remains small as usage grows, while Zcash and Monero unfortunately do not scale quite well. The amount of data one needs to store and actively use is growing with every single transaction and cannot be easily pruned. Finally, zkVM, like Stellar, is designed for issued assets, while Zcash and Monero networks with a single native asset. We have covered a lot, so let's summarize. zkVM is a blockchain protocol with practical confidentiality solution for real-world requirements. Its smart contract architecture is based around lightweight stateless VM, where contracts follow the object capabilities pattern and assets are native linear types. The cryptography that we need is implemented in pure Rust, cleanly and with record-breaking performance. The design is scalable, transactions are compact, fast to create and verify, and the blockchain storage is compressible. Complexity of the higher-order protocols lies off-chain, removing unnecessary load from the nodes and making the core protocols simpler. So there is much more to learn. ZkVM is a part of a Slingshot project maintained by Stellar Development Foundation. You can find complete specifications, roadmap, documentation, and code all in one repository by this address, and it's fully open and we invite you to participate. You can also try out the demo app at zkVM-demo.stellar.org. Thank you very much, and we still have a few minutes left for the questions. Hey.
All right.
Cool.
Let's make you big. We can close the video down. Let me just do that. Do you want to continue with a small, short presentation now, or do you want to do some Q&A?
Yeah, there was a little part that I missed in the initial recording and it was a bit too late to update it. So I can say a couple of words about the cryptography stack that we have. It will take like a minute and some performance considerations. And then, yeah, I'll be happy to take questions. So let's share the screen. Here we go. All right. So a couple of words about our stack. The whole thing is based on the Curve to 5519 Dalek implementation that offers the Edwards curve with the very high-performance vectorized operations that we have, which is the basis for all the performance that we're proud of. On top of that, there is a ristretto group which implements the correct prime order group because you're not supposed to actually use Curve to 5519 as is because of the cofactor. So for all the fancy protocols out there, bulletproofs and such, you need the prime order group. So ristretto gives us this. Using it, we've implemented bulletproofs. It's also part of the Dalek project. And it gives two APIs. One is for range proofs only, and another one is for the whole constraint system API. This is pretty kind of powerful thing that we have. And using that, we're kind of getting closer to ZkVM project. We have two pieces. One is the cloak protocol, which implements the mixing of some number of assets on the inputs and into some number of assets on the outputs. That does this in zero knowledge, meaning that you don't know the distribution of assets, but also makes sure that you cannot transmute assets like dollars into euros or create negative amounts. So Cloak makes sure that the network rules of integrity are maintained while offering you confidentiality in terms of directing the asset flow. At the same time, we use the same constraint system in bulletproofs to create custom constraints within the contracts. And to do that, we use the instructions of the ZkVM to drive this. So the cloak is one instruction, and all the other instructions allow you to do the custom formulas that you use in the contracts. Finally, on top of all of that, you can build your own protocol. So you're interacting with this whole stack through instructions of ZkVM. And the cool part is that the whole stack is written in the pure Rust. So everything is compiled very neatly, optimized, and also every layer is sitting on top of the Rust API, which is powerful and type safe, unlike, for instance, C APIs. So the whole stack is pretty complex and tall, but still it's a very little amount of code, and everything's easy to audit and read from bottom to the top. And the whole system was designed with performance in mind from the beginning. So here's the cool part. The VM has two categories of instructions. Some are very cheap, so it's really just like parsing a transaction. But the expensive operations are all uniform. It's some elliptic curve operations, scalar point multiplications. And all of these expensive operations are deferred. So the whole system is designed to use these operations only to verify something. For instance, verify a commitment, like a taproot commitment, or verify a Schnorr signature, or to do the bulletproof verification. So all of these instructions, they're uniform from the perspective of Ristretto group, and we defer them and verify together in a batch, which gives tremendous savings. So as a result, what we get is something like less than a 1 millisecond on a 3 gigahertz Intel CPU with the latest IFMA instructions. And the cool part is that this performance is consistent, meaning that the range proofs that you have to do in the outputs to prove that the numbers are not negative, they dominate the performance, and all your custom constraints in the contracts, they kind of come for free, unless you build something super complicated in the custom contracts. So your performance characteristic is pretty predictable, no matter whether you use the contracts or not, really. Also, the transaction signatures are always aggregated, so you don't have a linear number of signatures. It's just a single Schnorr signature for the whole transaction. Again, as I said, we have batching, and the transaction size is pretty compact. So we have roughly 1.5 kilobytes for the zero knowledge proof, which scales logarithmically. So even if you have a giant transaction, it will be probably less than 2 kilobytes. And for all the commitments, for the asset type, for the amount, in total, for input-output pair in a transaction, you would have to spend around 160 bytes. So a small transaction with a couple of inputs, couple of outputs would have a total of 320 bytes for just this data plus the proof. And then if you aggregate transactions in something like CoinJoin, then the marginal cost of the proof will go down, and only these commitments will dominate, which is kind of comparable to the size of Bitcoin transactions. And finally, CoinJoin is interesting here because it's a rare case where cryptography and privacy-preserving protocols are aligned with performance. You're incentivized to do coin joins because you're also saving in terms of size of the transaction and performance of verification. So you don't have to make a trade-off between privacy and speed. It's actually faster and cheaper to make transactions that are more private by using CoinJoin. So that's a cool property of the system. Yeah, that's basically all I wanted to add to the talk. And now I'm looking into the questions.
Yep. Also, Oleg, I'm going to have to bounce out soon to get our next session set up. Mm-hmm. We're running about 15 minutes late, but you should be able to continue here. What will happen mm-hmm. is I'm going to start the new session at 6:45, so that's in 3 minutes. But anyone, if you want to keep answering the questions, or if anybody would like to come back into this session, Oleg, you just stay here, and you should mm-hmm. actually be able to play this. You should be able to continue on this session as long as you need to. But I'm going to go get ready with the next presenter.
Sure. Thank you, Anna.
Cool. Also, just one thing, when you start answering those questions, hit start answering, because I believe that then when people come back to this, they can actually find out exactly where you answer the question, like in the video itself. So just click on start answering and then end with stop answering when you finish the question.
Oh, well, where is that button?
Do you see in questions? Ask a question.
It's a separate panel. Oh my God. Okay, I missed it. Now I see.
Those are some good questions. Okay, good. I'm glad you saw that.
Okay, good.
All right.
Great.
See you soon.
Thank you. Yep.
Bye.
See you. Okay, so the top question is, yeah, where do I click the button? Okay, so what's the rationale for using CoinJoin for graph privacy instead of another solution? Well, kind of the central consideration was the scalability of the state, right? So if you raise the link between inputs and outputs, like Monero does, where it kind of does it partially with the ring signatures, or Zcash, where you do it fully with the full anonymity set of the entire collection of privately committed coins, you no longer can use the UTXO set, meaning the set of unspent outputs, because you don't know which ones are unspent. So you have to kind of inverse the problem. You have to remember the spendings so you prevent the double spends, right? And this scales much worse because there's not yet a good good cryptographic accumulator to make this efficient, especially in a setting where you're not proving something to a central server, but you have to prove this to like arbitrary third parties. So the best that people came up with is a set of nullifiers, which is kind of exactly the same for Monero and Zcash, although their approaches are completely different. But the common thing is that you have to remember some piece of data to make sure that it's like uniquely tied to some coin, and it's not showed up in the blockchain again. So you simply just remember all of them, and this set grows linearly, and it has a pretty bad, from the caching perspective, pretty bad cache access pattern, right? Because you need to access the set randomly. So effectively, there is you cannot say that, okay, the recently viewed items are more likely to be accessed, so we'll store them in fast, expensive memory, and everything else goes on a spinning disk. So like we don't care how much they take. This is not possible because every new key image in Monero or every new nullifier in Zcash is a random number that could be like anywhere. Of course, you will have some kind of like tree and logarithmic access to it, but you have to logarithmically access the random points in this whole state, which grows linearly with every transaction. While UTXO set does not grow linearly. It kind of grows linearly with the number of wallets, but not the activity of transactions. So if you use the UTXO set, you cannot automatically raise the graph, but then you can compress it even further and then make the system much better scalable, because you don't okay, the sound is still on. Yeah, because you don't have to think about the storage costs. So in case of zkVM, we use the UTXO compression as a built-in protocol rule. So the storage is actually logarithmic in the number of UTXOs, which is great because now you don't have to worry about how much state you're wasting. There's no notion of dust outputs, nothing like that. So you can create as many contracts as you want because it's only you who have to like track their presence. So this leaves you with basically only one option: to have the coin join to kind of increase your anonymity set during the transaction, to join multiple payments at once. But again, this seems like a kind of cool approach because it also allows people to make transactions cheaper by saving on the size of the bulletproof proof. So that's my answer on that question. So how tightly coupled zkVM to the bulletproof proving system? Well, it's pretty tightly coupled because the constraint system is a part of the VM state. So effectively, almost like half of the instructions, they modify the constraint system, right? So if you say, okay, I want some condition to be verified in zero knowledge, then these instructions are operating on objects called expressions and variables and commitments, and they all amount to creating some linear and multiplicative constraints inside the bulletproof constraint system. However, it's going through the R1CS API, so in principle, the whole zkVM system can work on some other R1CS framework if we have it later, but it must be a system without trusted setup. Oh, by the way, like, do people hear me right now? Oh, yeah, thank you. Yeah, so on one hand, it's not like tied specifically to the bulletproofs, but to the R1CS API, but it needs to be without a setup, because when you verify a transaction, it builds the constraint system on the fly, and if you need some pre-processing or some kind of trusted ceremony to do that, that would not be possible with zkVM. So far, the system that can do that is the bulletproofs, but maybe in the future there will be something possibly better, and then it could be kind of swapped out from under, provided you have somewhat similar R1CS API. Third question: is Stellar going to provide any custody solutions for users to custody their state? I don't quite understand this question. Whether Stellar would provide, well, I mean, in general, whether Stellar would provide some, infrastructure for users to, store their valuables, I'm probably not in a position to answer this question because I'm not, working on that kind of infrastructure. I'm doing the protocol design. So I think it's better to ask this the like evangelist team or someone who's kind of working specifically on Stellar ecosystem. So fourth question: is it possible for zkVM contract to interoperate with another contract and read and write like Ethereum? Yeah, so there is some limited ability to do that because the contract can have an executable program embedded in it, and it could be either statically linked, like embedded in the taproot, or it could be dynamically linked, like provided as a signed program tied to that contract instance. So there are kind of a couple of ways this could be exploited. You could form the program that claims another contract. So it will be kind of nested claims. So first you claim the outer contract and say, like, okay, this exists. I want to take it from the UTXO set. And then when you show up, the branch in the contract and it's being executed can claim some other contract. And the contracts, they kind of implement the object capability pattern. So you cannot just do whatever you want. You have to interact with the contract, kind of call into it, and then if you satisfy its conditions, then it will give you some valuable objects, kind of leave it on the stack for you as an outer program that interacts with that contract. So you can kind of compose one contract claiming another one. Also, you could have signed programs that are kind of more flexible and can be applied to different instances of the contracts. This comes up with a payment channel example where you want to have some signed agreement about the new sequence number in this payment channel that you can apply to bump the state of your payment channel from wherever it is. And you can use a single, in zkVM, you can sign this predicate or this piece of program, not tied to a unique instance of the contract, but tied to some anchor point agreed by the parties. So you can apply the signed predicate to whatever state your payment channel is in. So to kind of rephrase this, the state of a payment channel is some contract in the UTXO set, and it can be changed when people contest and try to kind of force close it. And those instances are all unique because they are uniquely anchored. But if you want to be able to kind of bump them with a signed predicate from any state of those, you can tie this or like bind this predicate to not the contract identifier, but to its tag. So that's why there's instruction called sign tag. So this gives you some flexibility in applying the kind of partially signed predicate to not this unique contract, but to some set of contracts. So that's another example of interoperability. But in general, you cannot just willy-nilly access random places in the global state and kind of call from one to another. You have to kind of compose the relationship between contracts first in the transaction, and then you will see deterministically what will be the result of it. And as long as all the contracts actually exist in the proper state, then this whole transaction can succeed. So compared to Ethereum, you kind of know 100% how, like, whether the transaction will fully succeed with the predictable results or it will be fully rejected. So it cannot kind of get stuck in some middle state because, during the executions, the state was not exactly as what you imagined it would be. For that matter, like Stellar has a similar issue as Ethereum because transactions can have this like intermediate failure mode where the kind of superficial checks were passed, but then you have to do like complicated operations, do lookups in the database, and then something has changed. Maybe some orders were claimed, and now some conditions are not satisfied, and your transaction would be kind of too expensive to verify to just not accept at all. So it's kind of partially accepted. It's stored in the blockchain, the fees are paid, but transaction is marked as invalid. So some effects are not done, but some effects, such as deduction of the fees from the account, those have happened. So this kind of situation is not possible with zkVM. There are only two states: either the transaction is fully deterministically applied or it's thrown away. And the last question is, how do you handle a situation where there is no other transaction to mix and coin join when there is only one transaction to process? Well, that's a sad state of affairs where you have one user, nobody uses the system. So I guess there's an answer like we don't handle it in any way. There's, in fact, we don't have the facility for coin join at all for a moment. So it's kind of theoretically possible, but we don't have the the wallet infrastructure to do coin joins at all for now. But in general, if you don't have any other transaction, then you either just wait till there is, or the network is not as popular as it should be. So if the network is not popular, then that's a bigger problem than not having someone to mix with a coin join. So we'll probably have to work on trying to make it useful and popular first, and then hopefully there will be enough bandwidth and enough users to actually mix with low latency, meaning like not waiting for users to show up for too long. Yeah, so that's all the questions I got. Please let me know in the chat or in the Q&A box whether there's something else we could talk about. Otherwise, it was a big pleasure to talk about this to you.